Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello everyone, my name is Marcin and I'm a second-year PhD student at the University of Edinburgh. And today I'm going to talk about the new additions to the probabilistic programming language called Tabular, developed here at Microsoft Research, which have been described in a recent paper accepted at the European Symposium on Programming. This work is partly based on my previous internship at Microsoft Research from nearly 2 years ago. So because not everyone here might be familiar with Tabular, let me start with a quick recap of the language. So Tabular is a schema-driven probabilistic programming language, so it differs from other similar systems in that the user doesn't actually have to write a probabilistic program per se, but rather just annotate a database schema with probabilistic expression, which express how we believe the data was generated. So the language is embedded in Excel, so that both the database schemas with the annotations are written in Excel spreadsheets, and also the inference results are also displayed in Excel, so that we could process them and perform some visualizations and so on. Tabular programs compile to factor graphs, so that we could perform inference on them using the infer.net probabilistic inference engine, which has various inference algorithms such as expectation propagation. So just to give you an example of how it works, here is the tabular code for the TrueSkill model, which is a probabilistic model for ranking players in online games. It's used, for example, by Microsoft in its Xbox games. So in this model, we have a schema with two tables. The table of players by default only has the player names, and the table of matches has stores the names of the two players which took part in a given match, as well as the outcome of the match, that is, which player actually won. And from this data, we want to infer the skills of the players. So in order to do that, we add an extra latent column to the players table, a column which named skill, and we assume that its prior is a Gaussian center at 25. And we also state that the win-won variable, which says whether player one won the game, was generated from this expression, which compares the performances of the players on a given day, which are dependent on the skills. So as you can see here, we can not only infer the skills of the players and the values of any latent columns, but we can also predict the values for unobserved matches. So now let me move on to the new features of the language which are presented in the paper. So first of all, this paper describes user-defined functions which abstract away some of the commonly used patterns in probabilistic modeling. For example, conjugate models, which I will show in a moment. Another addition is the presence of user-defined queries, which can be used for computing deterministic data from inference results. This can be used in performing decision theory, for instance, on the inference results. I will also show an example in a moment. And the final contribution is a dependent type system with array bands, with array sizes and integer bands, which might depend on previous columns, together with a lattice of levels which separate the deterministic, the probabilistic, and the query level columns. So let's start with queries, and to illustrate how they work, let's consider the TrueSkill example again. But this time we want to decide whether it's worth placing a bet on one of the players participating in a given match, given the odds for this player. That is the amount of money we get for every pound we bet on that player. So in order to determine whether a bet is worth placing or not, we need to know the probability of player one winning the match, which can be inferred from previous match data, And we also need to know the odds, that is the amount of money we'll get if the player wins, which is known because it's an input. So in this example here, if the odds for player 1 winning are equal to 4, then the expected utility of placing a bet, that is the probability of the player winning times the odds minus 1, because we normalize it by the money we bet on the paper on the player times the probability of player 1 losing. The expected utility is positive in this case, which means that the bet is worth placing, even though the player is actually unlikely to win the match because the probability of it winning is only about 30%. In the second example, though, because the odds are only equal to 2, the expected utility becomes negative, and so the bet is not worth placing, which means that we choose not to do it. So now let's move on to the functions, and to illustrate how they work, let's consider the data set containing the data about the eruptions of the Old Faithful geyser in the Yellowstone National Park. This data set contains the durations of the eruptions and the time we have to wait for them. And as you can see from this graph, this geyser has two kinds of eruptions. Some of them are shorter, but we also need to wait shorter for them, and others are longer but occur less frequently. And we want to cluster these eruptions into these two groups, and also infer the distributions of waiting times and durations for eruptions in both groups. So this can be done by writing a tabular program with function applications, which can be combined with indexing, which was explained in a previous paper. So now let me show you how functions actually work. So in this example, let's focus on just the eruption duration for the moment and forget about waiting time, because it works in the same way basically. So here we have a function which represents the conjugate Gaussian model, and then if we assume that the eruption duration was drawn from this conjugate Gaussian model, then we can represent it in a program by a single line, which is a call to this function. And when we call this function without any parameters, then the default hyperparameters, which are the mean and precision of the Gaussian prior of this quantity, are substituted for these variables, and then we chop out the hyperparameters from the table and substitute the output column with the body of the function. So it basically looks like this. In this way, we can expand the function calls, so and reduce an extended program written in the extended language to one in core tabular, which directly corresponds to a factor graph, and on which we can run inference. As I mentioned before, function calls can be combined with indexing, which was indexed before, which was mentioned before. And let me show you how it works on a simple example. So in this case, we actually want to. So just wanted to mention that in this simplified example, we were not doing any indexing because we didn't want to label the points. We just wanted to infer the distributions. That was a simplified example, which was just meant to show how function applications work. And if we actually want to label the data, then we need to combine this call to the conjugate Gaussian model with indexing. So what this guy does is essentially it just creates two copies of all these static columns in this function. So we have two means and two precisions, one for each cluster, and then the final outcome returned depends on this additional index variable, which is drawn from another distribution. so in this case, we can have separate parameters for these two clusters of variables. And another contribution which was made in this paper was the presence of a dependent type system together with a simple lattice of levels, which I will talk about shortly. But for now, let's concentrate on the dependent types. So as I mentioned before, we can now have arrays of specified length, which might depend on previous columns, as well as bounded integers, which are always known to be always smaller than a certain quantity. So, as an example, consider the conjugate discrete model shown on this slide. This model has two inputs. One of them is the number of the band of the integer, which is meant to be drawn from this distribution, and this, which is also the size of the parameter vector from which we're drawing an index. And the other R is the variable representing the counts of the data. That is how much confidence we have in the results. So as you know, as you've noticed, we know by assigning a dependent type to this column, we know that the variable drawn from this distribution will always be an array of n reals, and the output drawn from the discrete distribution having this v as a parameter will be an integer up to n. So because the types are checked statically, users can discover some basic errors without actually having to run lengthy inference, and in that case it saves time on debugging and allows for some common mistakes to be spotted earlier in the development process. So moving on to the lattice of levels, as mentioned before, this new version of tabular introduces the query operator, which allows for the infer operator, which allows for deterministic or rather pseudo-deterministic quantities to be deduced from distributions of random variables. So now we have three types of columns. So we have deterministic columns containing input data or transformed input data. We have random columns which are assigned probabilistic distributions, and we have query level columns which contain post-processed data, which depends on the results of inference. So we have a lattice of levels which organizes a schema into these three levels. And in this lattice, we can use a deterministic variable whenever a random quantity is expected, or a query quantity, but not the other way around. And we cannot mix random and query level variables, and the only way to pass information from random distributions to query level columns is via this infer operator. In this example, this is an example of an error in which we want to decide whether to place a bet, as in the previous example, but this time drawing the decision randomly from a Bernoulli variable. But because this p is a random variable, and place bet is a query level variable, we can't. This doesn't really work because this has to be determined by inference, and this has to be determined by. Sorry, I wanted to say that. This variable depends on inference, and the distribution of this should be actually computed by inference. So we can't have this kind of dependency, and hence the type checker throws an error. So just to show you that tabular can actually be successfully used in practice, we have some early adopters of the language who used it for real-life modeling. This example shows a model used by Dylan Hutchison and Matthew Smith in their study concerning the recognition of wild and artificially propagated plants. This model, written here in tabular, can be used to deduce whether there's something suspicious about the plant. For example, whether it seems to be collected in the wild, even though it was declared to be propagated artificially. As you can see here with the results, which are the results of inference seem to be fairly accurate. This data was obtained by testing the classifier using five-fold cross-validation against labels assigned by experts. So what's actually in this new paper? In the paper, we have the detailed syntax of the extended language with function and queries. We have a reduction system which reduces tabular queries into core tabular queries, which have straightforward factor graph semantics. We have a dependent type system, and as I mentioned before, we have a measure theory-based denotational semantics and an example application based on Bayesian decision analysis. And the key theoretical results from the paper are firstly that a well-typed tabular schema reduces to a well-typed core tabular schema with the same type, and secondly that if a core schema is well-typed and the input database conforms to it, then the output database as returned by the semantics will also conform to the schema. And in future, we want to concentrate on model criticism, on determining how well compiled models conform to the data. We want to compare the performance of tabular against systems aimed at similar target user group, and we want to conduct some usability studies to determine whether the new features added by the language are actually helpful, and what else we can do to make the system more usable. And we're always looking for new both external and internal adapters of tabular to receive any feedback we might get. Thank you very much for your attention.
So, any questions? So I have one. As an user, if I want to define a new kind of distribution, for example, not Gaussian but student T, can I do so by specifying the density, or?
I don't think specifying custom distributions is supported in the current version of Tabular. However, I believe that the range of distributions which are available by default is fairly broad.
Mm-hmm. Okay, thanks. Any more questions? Yeah.
Could you say something about the efficiency of inference, sort of underlying?
I don't have the exact results, but as far as I remember, it was comparable to the efficiency of the infer.net system itself, and the code is also much more concise. So there is a little bit of performance deficit in comparison with infer.net, but it's not really that significant, and it's less than the amount of conciseness we get by using Tabular.
Okay, thank you, Marcin.